Alrighty, so welcome back. We're going to start talking now about the first law of thermodynamics, and so this is where we are in our notes right here. Again, if you have any questions so far, feel free to jot them down here so that you can ask them in class, so that as we talk about it, we work through the example problems and all the other activities that we're going to do in class, you've got that information ready to go. So please make sure that you're doing that, all right? Okay, so let's switch to, all right. So first law of thermodynamics, here comes the text. Whee! All right, so here we go. First law of thermodynamics tells us that energy can be converted from one form to another. From one form to another, but it is neither created nor destroyed. Okay, no, let's go down here. Created nor destroyed. And so this goes back to what we talked about when you were in intro chem. So energy is conserved. That means we can switch it from one side to the other or one type to another, but we're never really destroying that system. The amount of energy that is current in our universe is what it is, and it's just being converted from one type of energy to another. And so that's really all this is telling us to do. Now, due to the fact that we are talking about heat and energy flow from one thing to another, we have to be able to understand what area we are talking about and where that energy is flowing. If we don't have a good picture in our minds of where that energy is coming from and flowing to, then we can't really discuss where any of the numbers that go with it. Okay? And so when we are talking about something in our class, we're going to talk about something called the system. And the system is the portion of the universe that we are studying. Usually it is a reaction vessel or a container of some sort, and when we're going to study how that energy system is changing. For us, we measure energy largely as temperature. And so in our systems, we're going to end up having a temperature probe and other ways to see what's going on. Now, if it's not part of what we're studying, if it's not that system that we're looking at its temperature, it's going to be surroundings. Okay? And so if it's not part of the system, it's the surroundings. And so in our situation, if it's usually it would be the heat system of a room, the air in the room. You could just talk about the universe as a whole. And so let me give you a little bit better explanation for that. Imagine you were making rice in a pot on your stove. Once the water with your rice in it is brought to a boil, you cover it, you take it off the burner, and you set it aside. And once you've got this done, all we're created about is the energy of the system, the heat that's inside that pot cooking your rice. Okay, the pot and the lid are going to feel hot to the touch, but what that means is it's releasing energy out to the surroundings around it. And so that's the surroundings in that case would be the rest of your kitchen. The system you are interested in is the temperature of the rice and the pot that you're cooking it with. Okay, now in our case, we are primarily interested in what are called closed systems. Okay, and so a closed system means that matter is not being exchanged between what you are studying and the outside world. So it's got a lid. All that we can transfer is energy, but not matter. Okay? Another type of system that we could look at, and we're not going to do that, would be an isolated system. And in an isolated system, both matter and energy cannot be exchanged. And so those are a good example would be your coffee thermos. Okay, it's not a perfect example, but your coffee, the matter of your coffee itself or your soup or whatever you're trying to keep warm out on your deer stand can't be transferred because it's got a lid on it. All right? And the reason that it can keep your soup or your coffee warm for so long is because it's got a vacuum around it and it won't exchange air. It won't exchange heat through the system, and that's why it stays warm for so much longer. Okay, and so that's one of the things that we're going to talk about and how that plays out. So now this is going to lead us into our internal energy discussion. Okay, and so I'm going to erase this. If you need this yet, pause it and do what you got to do, but I'm going to erase. So here we go. Okay, and so in order to really understand what's happening, we need to have a better understanding even further of the other pieces and parts that we're going to use. So here we go. The internal energy of a system. So the internal energy of a system is the sum of all the potential energies due to the bonds plus kinetic energy for motion of the particles inside it. Okay, and so when I talk about kinetic energy of particles, so we know that little gas particles are moving all over the place, right? Because you guys, we talked about this last year. And so if we have a little sealed container here, okay, and we've got little particles zipping around, so we've got the kinetic energy of those molecules that adds to the total energy of the system. But if these guys are, I don't know, let's say they're bromine molecules, okay, there's inherent energy in that bond holding those two bromine atoms together. All right, and so that covalent bond has to have some inherent energistics in it, otherwise it's just not going to, it wouldn't stay together. Okay, so anytime we talk about the energy of a system, that's what we're looking at, is the sum of those two components. Okay, now we're going to talk about thermodynamics, but we got to have some qualifiers. Okay, so the first thing we have to do when we're talking about a thermodynamic quantity is we have to have a number. Okay, because without a value we can't do our math, and that's what we're looking for, is we want to be able to do math, because that's what chemistry is. Okay, we need to have a unit. Okay, now more than ever, a number without a unit is essentially useless. But the more important thing that a unit does for us is it tells us the scale of what we're working with and how we can continue to do what we're doing. And so the unit tells us that, whether it's in, I don't know, kilometers or millimeters, that tells you about the scale and the magnitude of what we're looking at. Those are really familiar units with us. We're used to working with those. But right now we're going to work with Celsius and Kelvin. And those are not familiar units, but even so, we still need to have a unit so we understand the magnitude and the scale of what we're working on. And then the other thing that we have to have is we have to have a sign. Okay? Okay, and I'm not talking about the here's your sign comic. I don't remember who it was anymore. I probably should have knew his name before I brought that up, but whatever. And so in our case, we're going to be dealing with systems that lose energy, would have a negative sign, and we're going to deal with systems that have a positive energy, which means that they would have a positive sign. They would gain energy. And so we have to know what direction heat is flowing. Okay? A good example of that. If you have a cup of iced tea sitting on your kitchen counter, okay, and it's super, super, super cold, it's a hot day, the air conditioner's not on, and that eventually that iced tea is going to melt all the ice inside of it, and you're going to end up with watered down iced tea. Okay, so in that case, the energy is flowing into the system to melt those ice cubes. Okay, now imagine you have a cup of hot coffee sitting in a cup on your kitchen counter. That hot coffee eventually is going to cool down. And as it cools down, that means that the heat that was inherent inside those molecular motions from your coffee molecules doing what they're doing inside that liquid, that heat is going to be lost as energy or temperature change as the coffee cools down and releases energy out to the surroundings around it. Okay? So if the heat is positive, energy is flowing in. If the heat is negative, the energy is flowing out. Okay? So you got to wrap your brain around that. Okay. Now, we're going to end up using some other stuff here shortly, and I'll show you what I'm talking about right now. Now, right here, the delta E. This is the change in energy. Delta E this is the energy final minus the energy initial. And so delta E is how we would say it. This should probably have parentheses around it. Which means change in E. Okay, so anytime you see the Greek letter delta, that means change. Okay, and we're going to talk about a couple of different units, a couple of different things that are going to be part of the Greek letter delta here. And so just so you know, that's what it means. So a positive delta E indicates that the system has gained energy. I just said this, but now we're actually going to write it down. And the overall total amount of energy in the system is higher than it was prior to whatever caused the change. Okay, so there we go. Now, again, you have your questions here on the bottom. Feel free to use those. Make sure that you do, if you have any more. Okay, I'm going to switch, and then I'm going to erase. Whee! And I could pause the video, but this is more fun for you guys. It gives you more time to laugh at my goofiness. So I'll do what I can, right? All right, now, a negative delta E means that the system has lost energy. So here we are. And to its surroundings, meaning that the system is lower in energy than it was before. Before the change happened. Now, the first law of thermodynamics gives rise to the following equation. Okay, and so what it says is that delta E is equal to Q plus W. And so delta E is the change in the internal energy. That's what that is. Q is the sum of the heat added or released, and W is the work done upon the system. Okay, now for right now, just hold off on this work done on the system thing. It's probably not going to make a lot of sense just yet, but it will as we work through this. Okay, so if I have a positive sign for Q, Q is the sum of the heat added. Okay, so if that is positive, that means that we are gaining heat. Okay, if I have a negative symbol for Q, that means the system is losing heat. Write it up here. There we go. Okay, W. If a W is positive, that means that work is being done on the system. And if the negative W means that the system is doing work on the surroundings. Okay. So I'll explain what that means in just a second. Now, if I have a delta E that's positive, that means that we have a net gain of energy. And if delta E is negative, that means that we have a net loss of energy for that system. Okay? Now, this is what's going to be what we're talking about when we say that we're going to be doing systems doing work. Okay? And so hopefully it'll make a little bit more sense here as we work through it, and we'll go through it. So I'm going to erase just a little bit longer here, and then we will move our screen here and keep moving. Okay, so when we're talking about the system doing work on the surroundings, the way that we do this in chemistry is we end up talking about basically one of these systems. It's like a closed piston, okay? So this part right here is the top of our piston, and this can move up and down. Okay? These guys are all just sealed. They're just really, you know, they're just the walls of the container. Okay? Now, imagine if we had some gas particles in here, which I have drawn for you. And so we've got some gas particles in here. And what happens if I stack a weight on top of this? Okay, so what happens if I stack mass on here? Wow, that actually looks better than it normally does. That's awesome. So think about it a little bit. If I put a mass here, this mass is going to put more pressure down on our particles, which means this bar is going to move down as well. And the particles, the distance between those particles is going to get smushed. We're going to compress those gases. So in this case, what that is that means that the surroundings are doing work on the system. We have found a way to increase the pressure on the outside so it decreases the volume of this space, and it's doing a work on the inside of the cylinder. Okay? Now, that's awesome. The other way that this could happen is if the other way that we can talk about this changing is if we heat this gas up. Okay, imagine if I put a Bunsen burner underneath here and I get the outside of this container hotter, and it's hotter and hotter and hotter. That energy is going to transfer through to these particles. These particles are going to manifest that energy difference by increasing how much they move. Their kinetic energy is going to increase. If their kinetic energy increases, that means that this little bar is going to go up. The space between molecules is further and further apart, and we're actually having this system do work on the surroundings because it's compressing the gases that are pushing down on my little system here. Okay, and so it's a little bit confusing, but I need you to try and talk your way through that and work your way through it. So here's a piston being supported by a cluster of gas particles inside the container. This is how we look at pressure volume work in chemistry. The container is the system this case, it is a closed system. As the piston moves down, you are compressing the gas and doing work on the system. Okay, I already said that. If the piston moves up, you are expanding the gases in the system. The system is doing work on the surroundings. Which I said that too. And energy is able to enter or leave the system as heat. Okay, now, cool. So this is the basic fundamental definition of what we're doing. So here we go. Now, if we are looking at a process in which the system is absorbing heat, heat is flowing into the system, that's a heat gain, we call that endothermic. Meaning energy comes within. Okay. If the system is releasing heat into its surroundings, it's a heat loss, we call that an exothermic system. And right there. That means heat is released. Okay, and so there we go. Now, last definition in this video here before we talk about is something called a state function. And so a state function is a property of a system that is determined by specifying the system conditions or states of temperature, pressure, etc. The value of a state function depends only on the starting point and its end point. And its end point. Okay, now the example that I have for you on this is, let's say you and a friend are meeting at the University of Wisconsin-Madison Terrace for lunch. Okay, you're both leaving Shawano at the same time. One of you is going to drive to the airport and fly to Madison and then catch a cab and go to the Terrace. One of you is going to drive to Madison and just meet you at the Terrace. Now, because it's a state function, all I'm going to care about is the starting point here and the starting point here. I don't care about the pathway that you took to get there, okay? So if we were to sketch this out, and I'll do it over here. So, all right, here's Shawano. Okay, here's Madison, okay? So here's Madison. Obviously this is not to scale, but you get the idea, okay? Somebody leaves in an airplane. So here's our little airplane, little engine. That's a really horrible diagram. Whatever, you get the idea. So here's our airplane. Let's say they fly to Green Bay, and they fly all the way down to Sheboygan, and then from Sheboygan they go over to Madison. Okay, so this is our airplane. Okay, all right, now from our driver, let's say our driver just goes over to Bondwell, takes 47 straight south, and there's a road that gets them all the way there. Okay, this is our car. Okay. This isn't real. We both know this, or we all know this, but whatever, you get the idea. Really, because this is a state function, all I'm going to care about is starting point versus end point. Okay? All I care about is the delta change. The end minus the starting point gets me where I wanted to go, and I don't give a rat's butt how I get there in between. Okay? Whether I drove or flew or went and did aerobatic techniques on the way, none of that matters. All that matters is the ultimate displacement here. Okay, and so we can talk about this in terms of other things too, but this is a fairly good example to help kind of point out what we're talking about. So here we go. That's the end of this one. Talk to you later.